Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. Which invertible matrices A in R to the n by n allow an LU factorization A equals LU without row exchanges, meaning Gaussian elimination can proceed using diagonal pivots without swapping rows? We'll justify the condition on the upper left blocks AK and fill in a missing factorization. No row exchanges means each step of elimination uses the diagonal entry UKK as the pivot. If that pivot ever becomes 0, the algorithm must swap rows, or it stops. These diagonal entries of U are exactly the pivots. Keeping them all non-zero is the whole game. We'll encode no breakdown up to step K using the top left K by K block. This is the standard criterion. Elimination without swaps works exactly when all leading principal submatrices AK are invertible. At stage K, elimination has only touched and depended on this leading block. These are the first K pivot locations, where we need non-zero pivots if we refuse to swap rows. Triangular structure forces those two zero blocks, upper right of L, lower left of U. That will lock in the form of the leading block of A equals LU. Multiplying blocks, the top left block becomes LKUK because the zero block kills the cross term. And since the top left block of A is AK, we get the factorization immediately. That's the missing expression. AK factors into LKUK. When no row exchanges are needed, every pivot UKK is non-zero. That makes each UK invertible, and LK with ones on the diagonal is always invertible. Product of two invertible matrices is invertible, so AK must be invertible for every K. Now go the other way. Assume every leading block AK is invertible. This prevents elimination from breaking at any stage. More precisely, if we run elimination without swapping rows, the pivot at step K is non-zero exactly when the leading K by K part hasn't become singular. Invertibility of AK guarantees that non-zero pivot exists, so the next elimination step is legal. So each step finds a valid pivot on the diagonal, and the full LU factorization proceeds with no row exchanges. The complete test is every leading principal submatrix must be invertible. The block multiplication explains why those leading blocks show up. The upper left block of A is the product of the upper left blocks of L and U. Visually, singularity of a leading block is the warning sign that a zero pivot will appear if you insist on not swapping rows. Next, we'll see what to do when a leading block is singular, how pivoting changes the game and keeps elimination stable. Watch the next video to learn more.